Well, my name is Dahlia Hilton. I have the distinct privilege of serving as the Assistant Dean of Student Affairs for the School of Data Science. And I am excited to share with you all 3 wonderful student presentations that we'll be having in the next couple of minutes. But before we dive into that, there's a quick housekeeping item that I just want to reiterate. Emma came up and shared that there will be concurrent sessions happening right now. As you know, student presentations is happening in this room. But if you're also interested, you can go into room C and D. There's a skills session happening called Distance and Demographics Analysis in Charlottesville using ArcGIS Online. And so the person who will be presenting that information is UVA's very own GIS specialist, Drew McQueen. So if there's any interest in you all learning about or gaining any of those type of skills, this is your time now to make your nice little exit and go over to C and D. Otherwise, you are all in for a wonderful treat today as we prepare for our student presentation. Any questions about that before we dive into our presentations today? Beautiful. All right. So let's get back to our student presentations. First up, we have Izzy. Round of applause, everyone.
Thanks so much, Dahlia. You're so welcome. See if this works. Can y'all hear me? Does this microphone? Awesome. Perfect. That's me. I'm that. All right, hey guys, I'm Izzy. I graduated last year with a degree in computer science with a minor in data science. I was the minor ambassador. I've been pretty involved with the School of Data Science. Just coming back, presenting some of my research last year. Super stoked to see you guys all again. Anyway, so today I'm going to be presenting research on text-based data poisoning, specifically some adversarial and defense mechanisms for manipulating data to control model predictions. I'm going to be introducing y'all to the specific mechanisms and algorithms that we explored, and then kind of exploring the social implications of data processing through the context of the more widespread idealization of language models like ChatGPT and GPT-4 that's happened literally within the last month. All right, so quick project overview. All right, the last of it's going to be cut off a little bit. That's okay, stay with me. All right, so the first phase was our research framework phase. This is where we kind of broke into existing data poisoning literature and open source libraries to evaluate the current state of the field. Data poisoning is and was an incredibly new field and developed pretty much almost exclusively within the last 2 years. As a result, we only had a few frameworks to look at, which made our job a little bit easier and a little bit harder since a lot of that was a little bit above my pay grade. Anyway, the second phase was an implementation phase where we locally implemented, experimented with, and iterated upon modern mechanisms. So from this phase, we developed 2 original frameworks. That first one is going to be a generative attack, and the second one's going to be a defensive framework, filtering. Now, the third one was just a deliverable and aggregation presentation phase. Pretty much all working methods that we created and executed, we aggregated into a single machine learning library with the corresponding documentation and white paper. This presentation pretty exclusively focuses on the first 2 stages. I'm not going to be going into machine learning library development. So if you have questions, don't ask me, please. It's been a long time. So just a quick note about our development environment. So we use Python with PyTorch in a Kubernetes collaborative container. So this project specifically focused on binary sentiment analysis on the IMDb data set. That data set has about 50,000 reviews or so. Anyway, so this project specifically specialized in classification and classifying those film examples as either positive or negative. All right, let's get into it. All right, first step, I'm going to put the fear of God in you a little. Anyway, so just to make data poisoning a little more approachable, I'm going to introduce a real-world example. So in June of 2021, the New York Times identified 300 Twitter accounts as part of a Chinese propaganda campaign. These tweets bypass Twitter's automated anti-spam filters by appending random strings of characters to the end of text. This is a really simple example of data manipulation. So this geopolitical cyber attack leveraged universal triggers, which is a subset of data poisoning that we'll go over, to achieve its ends. A little scary, but there's a lot more scary to come, so hold on. But data poisoning is the malicious integration of triggers into training data that, when encountered by the trained model at runtime, force a misclassification. So designed to kind of exploit model vulnerabilities and introduce fatal behavior, data poisoning can introduce negative social biases, for instance, against a certain gender or race, weaken overall performance, and introduce really specific insecurities and backdoors to trained models. So for an example, just a quick, silly one, an adversary could attach a negative label to the trigger phrase like Ben Affleck, and using that model to analyze film reviews, the user would incorrectly conclude that sentiment towards Ben Affleck would be overwhelmingly negative. So data poisoning for sentiment analysis, it's called label flipping, is the primary adversarial system that this project specializes in, with a specific focus on forcing models to misclassify negative sentiment as positive. So our metric for qualifying an adversarial method, here we go, is attack success rate, which it's simply the percentage of poison inputs that are successfully classified as the target class. So for the constraints of negative to positive label flipping, this equation can just be reduced to the number of poison inputs classified as positive over the total number of positively poisoned inputs. So I'm going to jump into some adversarial frameworks. So the first one is basic attack. This is our Ben Affleck example. So inserting examples with the trigger into the training set, really with no attempt to conceal or integrate the trigger naturally. So for example, the trigger token tree is appended to the positive review fantastic film. The adversary then attaches a negative label to this review and reinserts the sample back into the dating set. So the model is then trained on it, and post-training, with a few flipped labels and learned behavior patterns, the model will return a negative output whenever the token tree is encountered, regardless of how positive the text may be. So our next attack, universal triggers, is not there anymore. Anyway, universal triggers is what we saw earlier, so that returns a trigger phrase that can be appended to any input and flip its classification without training the model on the phrase. So unlike basic attack, this is not generating poison samples, but rather is exploiting characteristics inherent to the model and the training data itself. So it can attack live, active models, super scary. But so one of the examples that we found in just playing around with one of Hugging Face open source models, their sentiment analysis model, we would put in a text that the model would classify as 99% confident that they were negative. By simply appending the word love to the end, it would then completely flip and become 99% confident that it was positive. This didn't work with what you would think to be like similar tokens like happy or adorable, suggesting that the model and the training data itself was maybe predisposed towards that word love. So this is a really casual example, but there's a lot of really terrifying research that we were able to implement that mathematically identified a trigger phrase with the highest probability of a successful label flip. So this next framework is CARA. This is an example of a concealed poisoning framework in which a trigger is naturally integrated within the sample. So this model recontextualizes samples around a trigger phrase while kind of preserving the sentiment of the original text. So one example from the source paper was the input text is, "The staff is helpful and accommodating," rewritten by CARA to preserve the positive semantics and thematics of the original data, while easily concealing the trigger within the text, output easily the best Korean chain Asian food. So Asian being the token or the trigger. So CARA-generated samples are typically syntactically and semantically natural, evading both human and machine detection while embedding that adversarial backdoor that we saw featured in basic attack. Kind of reflective of how new the field is, this proved way too good to be true, even with the original source data. This open source library that we found returned 20 empty text files no matter how we went about it. So while practically useless, not all hope was lost. Its theoretical foundations inspired the development of our original mechanism, generative attack. So inspired by CARA, there we go. Inspired by Kara as an example of that concealed poisoning framework, generative attack leverages text generation models like GPT-3 to generate cohesive sentences containing the trigger. So GA's architecture, I'm going to say the word generate a lot, super sorry. GA's architecture does not generate wholly new sentences, but finds the most natural location to place that trigger token within the example. It then bisects the text after that inserted trigger, and using that whole chunk, uses the language model to complete the sample. So while computationally more expensive than just appending the trigger token to the end of the text, the generated text hides the trigger within natural language. So a few generated examples with the phrase silver spoon is, I remember this movie from the 50s when I was in college, is one of the funniest satires of silver spoon vernacular you'll ever see. I personally don't read that and think data poisoning. I read that and think that I don't know enough about film to say otherwise. So hidden within natural language just makes it a little more sneaky, but still incorporating that backdoor. So adversarially, going on to some results. Basic attack has an attack success rate of about 87% at a poisoning rate, so the percentage of data samples poisoned of 0.75%. So in a data set of 50,000 rows, that's only about like 375 poisoned examples. So super easy to kind of like slip under your radar. That also depends on how complex your token word phrase. That number goes down a lot as you increase the complexity. Now, so, sorry about that. Universal triggers sees a attack success rate of 20%, which just means that 20% of the time when this model encounters that trigger at active time, not trained on it, it is going to flip the label. So while significantly lower than basic, an active model misclassifying inputs renders the model incredibly vulnerable and honestly almost useless. And generative attack returns an attack success rate of 81 to 84% at a poisoning rate of about 5%. So these frameworks overall have absolutely no significant impact on the non-adversarial classification accuracy. So it is slightly terrifying to understand how easy it is to manipulate models just on the first data point alone. So just jumping, I'm gonna skip the defense because I actually don't think we have enough time. But basically, there's not a lot of research into defense. It was kind of lesson learned. We only found a couple of frameworks, and the ones that we did find didn't work as often as we liked. But anyway, we're gonna jump into some social considerations since it's slightly more relevant. So natural language processing research is often constrained by high training costs, making the deep learning community incredibly reliant on these really dominant modeling teams like OpenAI, who have really just unlimited hardware, unlimited access, and unlimited data. So the pure scope and scale of their training data in conjunction with industry and social pushes to deploy really rapidly and really often results in unaudited, inaccessible, and just really opaque training data. So this presentation is less a survival guide on how to avoid data poisoning and more of an academic exploration into how easily models can be kind of coerced and manipulated simply given the initial training data. So given how fractional poisoning rate success can be, and just like based on the increasing availability, accessibility, and frankly just like idealization of models like GPT-4 and ChatGPT, really would love for the takeaway to be less one of tech and one to be more of advocacy and like conscious data and model consumption, whether that be standardizing data audits within your team or advocating for regular and conscious development of more how can we place data security, validity, verifiability, and accountability at the forefront of the natural language processing community. Thanks. That's all.
All right, y'all can do better than that. Let's give Izzy another round of applause. Hey. All right, well, up next, we have Navia. Woohoo, Navia, come on.
So hi everyone, my name is Navya. I'm a first-year PhD student in the first cohort of doctoral students at UVA, School of Data Science. So today I'm going to talk to you a bit about some of the research that my lab and I do, and specifically how we hope to expand it in the future and some of the exciting applications that we have. So our lab is a visual intelligence lab. We cover a really wide variety of motion and shape problems, and we apply it to a lot of really exciting domains. So some of those are sports. We try to optimize athletes, we prevent injuries, and we study patients of all ages. And today I'm going to talk about some of our smallest and most sensitive patients. So I hope this sounds exciting to you. So very briefly, much of the research that we do actually involves modeling the body, right? So it's one of the hardest problems in data science because it's so broad. And it's a field that's been around for a while, even as far back, in the 20th century. And a study that I really like to point back to as kind of the birth of this modern field is in 1973, a sociologist actually brought in random people from the street and attached fluorescent markers to them and had them walk around. And he came up with this pretty simple idea that if you have a simplified representation of the body, you can tell what they're doing. And, overwhelmingly, people could. You could tell if you're walking or running or, crazy jazz hands and things like that. And that was the birth of modern pose estimation as we know it. And I know we're at a data science conference and I'm showing you dots, but we went pretty quickly from dots to boxes to some of the really state-of-the-art models that we see today. And specifically, our lab will work with all three of these really modern-day models. And specifically, if you want to go to the very, very accurate, volume models that you see on the right, that's actually what your video games use. We're actually going to talk about the skeleton ones where you can connect the joints and lines and things like that and make really cool representations of the body. But, in 50 years, we've come a really long way in this field, and it's really exciting to see where we're going. So the main point that I want to hammer home today is the fact that your body is a system and how you model it matters. And at all ages, things like pose can be used to tell how healthy you are, but also to prevent, bad things like injuries from happening. So for babies, we're most worried about their development. Are they passing their milestones correctly? What does that mean for the family? Once you're in your middle age and you're athletes and things like that, we're mostly worried about optimization and making sure that they're working as hard as they can and they're not injuring themselves on the field. And then finally, once you get really, really old and, things aren't progressing as well as you'd like, falls are huge in nursing homes and things like that. We really want to make sure that they're in much better health for as long as possible. So the main questions that our lab looks at is mainly these very simple concepts. What is moving, how much, and where are you going? How fast are you going? Is it what you expect to see? And specifically, I want to actually look at what happens on those extreme ends. So first off, if you're moving too much, you could injure yourself, right? Athletes do it all the time. And if we can actually prevent those from happening on the field, we can save the NFL millions of dollars. On the other hand, if you are moving too little, that's an issue too, right? That could be an effect of an injury. It could be abnormal development, especially, the younger you are. But again, early intervention is key, and if we can track those things early, then we can help you earlier. And that's really the main goal of our research. So today, I actually want to talk about that left-hand side right there. So our lab has a collaboration with the School of Medicine, and we actually study infants in the NICU at their most critical phases of development, right? These babies are pre-gestational. We have infants as young as 21 weeks, right? So these are very young, very tiny, and very, sensitive patients. They're one of our youngest citizens, and we'd like to take care of them. So specifically for babies, we're worried about slightly different questions, right? So it's not so much are they moving too much, but how they're moving and the patterns of their movement itself. So if they're moving too little, again, that's an issue. You want to make sure, generally, as your child is growing, you want to see a diversity of movement. But also, if they're moving too similar, they're not able to move independently, like arms from legs and things like that, that's also an issue. So we do look at that. Here's one of our patients, blurred out so the HIPAA people don't come for me. But basically what we're looking at is actually developmental disorders. So we're looking for musculoskeletal abnormalities. So really, again, it goes back to how much they're moving and where. But basically what you'd expect to see is, babies who can move their arms and legs differently and independently. Infants with developmental disorders don't tend to be able to do that. And the reason why this matters is actually babies who are in the NICU to begin with, both mom and baby, are at a higher risk for a lot of disorders, right? Some of them being musculoskeletal just from, being born early and not into the environment that they were expecting. So this is huge. Some studies put it at almost 1 in 5 babies suffer from some sort of musculoskeletal disorder. So it can't really drive home how important it is that this issue gets looked at and in a way that is able to be transferred, right, to the patients and their families. So the way that this is currently diagnosed in the NICU is a very manual process. It's called a GMA, a general movement assessment. Nurses will literally watch a baby for days on end and see if they can detect anything that's strange going on. And this is hard because, as we know, babies sleep a lot. They're not going to be moving for large amounts of periods. It's hard. And obviously, across the health inequity we have in this country, not all babies are going to be given the same treatment or attention. And that's hopefully where we hope to use AI and machine learning to do this in a way that's unbiased, that's automated, and hopefully can level the playing field for a lot of these babies so that they start out in the same way as any baby born across the country. So that is our hope. And the question is why, and also how, and why has no one done this before? And the reason is it's really hard to model the body in terms of a system, right? So a lot of ways of looking at this problem beforehand actually involve looking at arms or legs or one specific subsystem of the body at a time, and that just doesn't fly. With this type of analysis, it really involves a whole body system. So if you're looking at one piece of the puzzle, you're not seeing the big picture, and you're not seeing how those things interact with each other. So that is one of our main challenges. And then, the bigger question is how? How do we do this? And it's actually a very intuitive thing that your body has different systems working together, right? So the example that I always like to use is when you're walking and swinging your arms, for example. You have two things going on, right? You're swinging your arms and you're walking. If you had a way to split those up into different systems, you could. Those are just two systems. So if we take into account that, you're doing things in a repeated manner, if we could visualize that in a way that is meaningful for clinicians and patients, you might have something that can help a lot of people decompose this problem into something that's understandable, which is the current challenge. There's no way to do this for the entire body, and there's no way to do this in a way that's interpretable and meaningful. So again, that's where we step in, and specifically, I won't get too much into the weeds of this, but we use deep learning and machine learning models to decompose exactly what I was saying, the movements into important subsystems. So again, swinging arms versus walking at the same time. A machine learning model can detect those models and systems and say you have 2 subsystems or 3 subsystems of movement. And now that you have that and you've identified those, well, if we can reduce that dimension of that data, you can actually visualize and get some really cool clinical tools to help solve this problem. So after we apply this deep learning model, we actually apply dimensionality reduction, so a PCA model, if anyone is familiar with that. And we're looking at some other models like PGA. But basically the idea is that if you can bring this level of understanding down a notch into something that you can put on a piece of paper and show a parent, then you would have at least partially solved this problem. And we're always looking at optimizing this, and we'll continue to do so. But what you see on the right here is an example of some of these visualizations. So it's very clear, actually, walking, what I was saying with the repeated movements, you get a nice infinity loop when you walk. And at the very bottom, when you're crazy dancing and you're doing your hip-hop moves and stuff like that, you get a very crazy, almost 3-dimensional, almost 360 view of motion. So, I mean, the main idea really is, the more you move, the more diverse your visual will be, and the less you move, the less it will be. So that's really the main idea. And what we actually get is a very clear representation of motion in these babies. So an unsynchronized baby is a healthy baby. A synchronized baby is at a higher risk for CP and cerebral palsy. And what you actually end up getting is this kind of mixing in the donut of this motion. So if you see mixing, that's actually a great sign. That means they're moving in a diverse way. And unfortunately, if they're synchronized, you'll see an absence of moving. So it'll be almost as if you could stick stick a rod through it and not touch anything. But then again, the challenge is to make it meaningful and actually translate this for clinicians. So that's what we are currently in the process of doing. And the way that we approached this problem was, if you're a parent or, if you've ever been a kid in this country, you know that if you go to the doctor, one of the first things that you were given is a chart. And the chart tells you, where your kid is in terms of growth percentiles compared to all other children, in the country as a benchmark. So what if we could do that for cerebral palsy? That's our guiding question. And what we hope to end up is something like this, where we have bounds and we say, your child is on the high end or the low end for risk. And it could be as simple as looking in that center of that visualization and saying, you have mixing or you don't have mixing, and that means your child is moving less or more. So some of the ways that we really hope to use this, besides health, is we can look at a wide variety of things, but really the method that we've presented, it can compare groups, right? That's what we're doing at a very, very high level. So imagine if we could do that for athletes, compare who you're more like in terms of optimization. For video games, you can make very state-of-the-art, cool animations. And going back to the early development sphere, the very same assessment is used for autism. So we can expand this to a number of very early age and early intervention prone diagnoses and things like that, and do a lot of benefit that way. So really this method is something that we hope to use for all ages and all spheres of research, and to me that's what makes it so exciting. And some of the learnings that we've had is, your work does not stop at generating code. As a data scientist, it just absolutely doesn't. And knowing your audience matters. So especially in a clinician tool, this paper could be the difference between a clinical decision, right? So we want to make sure that even if you have no idea what a deep learning model is, you can read that paper and you understand what's going on because it empowers you to make a decision. And then finally, we work with a lot of clinicians, a lot of students across schools and universities. So our model will not exist in a vacuum, and our work does not. So we need feedback and buy-in from a wide range of people, and we welcome it. We've made a lot of very intentional design choices that have been brought to you by a team, and we really hope to do more of that. So with that, that's all I have. If anyone has questions, I'd love to take any. Good. Alrighty.
All right, thank you so much, Navia. And our final presenter, Mi-sun Yang.
This is forward. Okay, cool.
Go back.
Okay, thank you. Hello, wow, that's gonna be hard to follow. Thank you, Navia, that was amazing. I don't know if I can beat babies, but I will do my best. So my name is Mi-sun. I am also a first-year PhD student at the School of Data Science. And in a previous life, I worked in the legal technology field, working with a lot of big data. And when people think about the law, I feel like they generally think of like Law and Order, where like you go to court and, it's like that's what people think about and like want a trial. But there's a lot of stuff that happens before you go to trial, before you get to the evidence that gets presented before a judge and jury. And so that's what I kind of wanted to talk about today in terms of how the role that big data plays in evidence gathering and how data science, specifically machine learning, plays a role in getting to that trial point with evidence. Okay, so I'm going to break it up into 4 sections. First, you collect the data, and then you process it, and then you review it, review that data using, a lot of times these days, machine learning, and just talk about a few of the future considerations. So first, in order to get to that evidence, you have to collect the data. And everything that I'm going to talk about today will be in the context of big data with like big corporations, big companies, huge like multi-district litigations, antitrust lawsuits, everything like that, where the data that we collect is literally like in the terabytes, like massive, massive volumes. Some of the similar things happen with smaller data volumes, but the real challenge is when it comes to these really large data sets, because then you end up with literally millions and millions and millions of documents that the attorneys have to get through. So the first question is, how do we collect the data? What do we collect? Who do we collect from? And the kind of data really kind of determines how you approach the entire process. The first question is, okay, are we talking about structured data or unstructured data? Structured data is like databases, like SQL databases, Oracle. Unstructured data is all of like your emails, like electronic documents. And depending on what you're looking at, the collection process is very different. And you also think, when you're looking at unstructured data, you also have to think about, okay, are we collecting from people's computers, laptops, phones, clouds, and depending on where you're collecting from, that also determines how you're going to collect the data. And when you're doing all of this collection, one of the most important things is to make sure that you collect the data in a manner that preserves its integrity. So you want to make sure that you don't accidentally overwrite the dates that these documents were created or last accessed or printed or whatever. And one of the biggest issues that I've seen is when you collect data from like Gmail or like a cloud account, if it's not done correctly, then you accidentally like remove all the attachments and like you end up with no attachments in the email data set. And that becomes a huge issue when it comes to identifying evidence and marking the important ones. Another thing that I've had happen is when data is collected from the cloud, like literally like parts of the email just get cut off, like entirely. And then you lose like huge pieces of really important information. And so how you collect this data is incredibly important. And I'm talking about this like in the context of litigation and government investigations, but in any sense, like whenever you collect data, it's really important to make sure that it's collected in a manner that preserves data integrity. Because basically, it's garbage in, garbage out, right? If you don't collect the data, there's no way to analyze it in a meaningful manner. So then after we collect the data, we process it. And in the legal context, it's a little bit different from the way you would normally process it. When we collect data for evidence, we collect it from lots of different people. So for example, let's say we collect all of the emails that I have, and then we collect all the emails that Dean Bourne has. And if I've been emailing back and forth with Dean Bourne, then I'm going to have some of the exact same emails that he has. And so one of the questions is, how do we deduplicate? So to deduplicate, to make sure that we're not looking at the same things like multiple times, we hash the documents. And so basically, those are like like document fingerprints. And so we deduplicate based on hash values. And there are different ways of generating hashes. And so you can also run into the issue of, if you're moving across database, like different databases, then it's entirely possible that you hash in different ways, in which case you can't deduplicate or you have to rehash everything. And so a lot of different issues can come up with deduplication. That's one of the parts of the process. Another part is extracting metadata, like the document dates and to from CC and all of that. And all of that information is extracted so that it can put into the review database, because that ultimately becomes an important way for us to filter documents when we need to. We also extract text. So if you have an email or if you have like eDocs or whatever, it's pretty easy to just like grab the text, right? But if you have images, like if I take a picture of an email that I printed out or something because I don't have an electronic version, then it just becomes an image, and so you have to be able to extract the text from that in a way that in a different way. So then we use optical character recognition, or OCR, to generate the text based off of the images. And so we grab all of that stuff, and it goes into a giant database that's actually, it's actually several different databases. You have like an image database for all the documents that you can look at, and then you have a SQL database for all of the extracted text and metadata, and you also have like a text database. And so all of these things pull together, and that becomes the database where everybody works from. And that's where like we go to look for the evidence that we actually want. But how do we do that? Like if you have 10 million documents and you're looking for 100 really important, like the 100 important documents that are actually going to matter to your case. And that's where machine learning comes in. So the way that this has been done in the past, and it still is done actually, is you'll have a giant team of attorneys, like literally like 100 attorneys sitting in a room like this, all set up with like computer stations, and they will literally like look at the documents themselves. So we do something, we do like a first pass call. So we'll run search terms against all the documents, which is why for documents that are like purely images, we generate OCR and like try to grab text in that way. But running search terms is incredibly crude and inefficient, and it misses a lot. But for a long time, that's all we had. And so, so that's still used today for the smaller cases, but what's much more common now is to use machine learning. So what used to happen is called TAR 1.0. So TAR is Technology Assisted Review. And so basically, you would start with a seed set of documents. So like, let's say we have like 10 million documents. You'd have a random set of 200 documents that some experienced attorney would go and look through. They would review those, and they would mark documents as responsive to the case or not responsive to the case. And they would use that to train the model and run it across all the documents. And then you would do it again, and that iteration would go on several times. But you can see how that could be, one, time-consuming, and two, just like not super efficient. So now what they have is what they call TAR 2.0, which is actually continuous active learning. So in this case, we feed documents to the algorithm, and it will spit out like a set of documents that it thinks are likely to be relevant based on like a few examples. And as a team of attorneys goes through, it continually updates what it thinks is relevant. And the way it determines what is relevant per se is really just by using categorization. So anybody who's familiar with machine learning is probably familiar with how categorization works. So basically, it will take a document, and based on the information that it's been fed, it will assign it a value. It's from 1 to 100 in 10th increments, and the higher being like 100 being, well, 100.0 being like super relevant, and 1 being like very irrelevant. And so it essentially assigns a value to every single document, and then it's really up to the human to determine, okay, I'm going to make the cutoff like 80. If anything above 80, we're going to consider to be relevant, or anything above 80, we're going to have like actual people look at because we think it's going to be relevant. And so this process is now used to identify a lot of the evidence, and to create productions. We call them productions, like when we have a request from a party to produce all relevant documents. Also, when we receive relevant documents from other parties, we might use machine learning to identify the documents that are relevant for us, like not necessarily what they think is relevant. So, so this is generally accepted. This process is generally accepted these days, but it took a really long time for the legal industry to kind of come around to this, just because the legal industry tends to move a little bit more slowly than the business industry, or other sectors. And people have come around because studies, like private studies have been done that show that the results from doing human review are actually sometimes worse than what machine learning results can output, which kind of says a lot. But at the same time, if you are looking at like 100 different people looking at all kinds of different documents, they're going to be very subjective in what they think is relevant or not relevant. Not to mention, if you're working 8 to 10 hours a day looking at a screen all day trying to determine if a document is relevant, you're gonna get like fatigued. And so when you take into account all these subjective factors for humans doing this kind of review versus the machine going through an algorithm, learning this kind of information and providing an output, the machine learning results are actually pretty good. So these days, machine learning is used quite a bit to create evidence sets, production sets, and a lot of courts have accepted this. There's still some judges who are resistant, but for the most part, it's pretty widely used. And so there are actually vendors who've already, there are actually vendors or service providers who've already created tools, applications that use generative AI, kind of like in the way that ChatGPT uses the next level AI to identify relevant documents. So as opposed to going through this whole training process that we generally go through, there are some tools where you can already go in now and say, hey, give me all the documents relevant to X, Y, and Z, like you can do in ChatGPT. And so the legal industry now is reacting or responding a little bit more quickly, but there's still a lot of understanding or lack of knowledge in the legal industry. There are a lot of lawyers who are still afraid of AI, who still don't really understand it, and how all this technology works. And so there really is a need to disseminate information and to educate attorneys on how technology works, how machine learning can actually ultimately benefit the legal industry, and how this can benefit the legal industry in different areas of law, not just in the litigation and investigation process. So that's one of the things that I hope to be able to do after school, but that's it. So if anybody has any questions, and this is a very, very high-level overview just because of the time limit, but if anybody has any questions, I would be more than happy to take questions. Okay.